this is a picture of STO1, which remember was happened to be an action groupoid of the complex numbers acting on the complex plane by exponentiation. And so the meaning of this picture is that this line is the complex plane, is the base curve. Okay, and these are the identity arrows of the base curve. And each point in this two-dimensional space is a groupoid element. It's an arrow. And it goes, the source of the arrow is given by the blue line intersecting with the base curve. So for example, this point here, right, or this point here, has source given by this point and has target given by this point. You just follow the red or the blue lines to show what the source and the target are. So this point maps from here to here, right? That's how it works. And you can see that the red and the blue curves, they become tangent to each other. They start to coincide the closer they get to the special point on the curve, which is the pole. The pole is located right there. Okay. Now, STO2, this is the one where you're acting by e to the uz times z. So it goes from z to, not to e to the uz, but e to the uz times z. And it has a different appearance. And so this point, again, source and target. So this one has an associated Lie group, namely the complex numbers acting on the complex plane. And this one does not. This one is a true groupoid, which is not associated to a group. I just wanted to show you what they look like. There's different ways of drawing these pictures by using changes of coordinates. So this is the same two groupoids, but where the source map now is completely vertical, and this target map is not vertical. So they just to give you an idea of what these things look like, I put them. We'll put these on the drive so you can look at them.
These are the real points.
These are the real points. Yeah, this is the real groupoid over the real line, which is just a real slice of the complex groupoid. Anyway, okay, so let's get to lecture 3. Lecture 3 is based on this paper that I wrote with my former PhD student Francis Bischoff and Maxim Zabzin, who's a physicist and who has worked on generalized scalar geometry for many years. He worked with Rocek and Ulf Lindström. He was a student of Lindström, and Rocek and Lindström were together with Hall and Gates. They were the ones who were at the origin of the study of the 2,2 sigma model. Okay, so let me just, let's begin. So in 1979, Zumino started studying some sigma models, maps from a two-dimensional surface to a Riemannian manifold. And what he observed, he was actually doing it first in dimension 4 for obvious reasons, but he observed that if you endow a target space with a complex structure compatible with the metric, then the model inherits a supersymmetry and goes to 2,2 supersymmetry in dimension 2. So this is I'm sure that most of you are aware of this, but in case you're not, the importance of this observation cannot be understated. I mean, physicists would not care about Kähler manifolds, Calabi-Yau manifolds, none of that, if it wasn't for this fact. This is the central observation, which is like at the interface between geometry and physics these days. Okay, and then a few years later, Gates, Hall, and Rocek, they realized that Zubino's observation was not a one-to-one correspondence. He did not prove that if you have this supersymmetry represented on the fields, it must be that the target is Kähler. He did not prove that. He just observed the reverse. He said that if it is Kähler, then you do get a representation of 2,2 superalgebra. So what they did was they realized that there was a different geometric structure which also gave the same representation of the supersymmetry algebra. And what they realized was that you could have the left moving fields and the right moving fields, they could see different complex structures. So the manifold actually, the target manifold has two complex structures, one of them gives the supersymmetry for the left moving sector, and the other gives the supersymmetry for the right moving sector. And that's why Rocek would used to tell me that it was like having a schizophrenic Kähler manifold, so that the left hand and the right hand are divided in this way. Okay, so what do you have? So what is this geometry that they defined in 1984? They have a single metric on M and two complex structures, I plus and I minus. Okay, and if we take omega plus, which is the combination of the metric with I plus, this is what would normally be the Kähler form. But dc omega plus, or sorry, so this would be the Kähler form, but it's not closed in this case. Okay. Instead, it satisfies this equation. So the two Kähler forms for the two complex structures are not closed, but they are jointly, they cancel each other out in a certain sense. So the derivative of one cancels out with the derivative of the other. And this derivative, dc, this is I del minus del bar. Now, so this is the other real operator that you get on forms when you have a complex structure. So this thing depends on which complex structure you use. So, furthermore, each one of these, so omega plus is a 2 form, dc omega plus is a 3 form, okay? And this 3 form is closed. And this is the Nevers-Schwarz 3 form flux, or the Vesumino 3 form of the model. Okay, so we get dc plus omega plus is equal to minus dc minus omega minus is equal to h, which is a closed 3 form. Okay, so that was the origin of what they were doing. They were interested in looking for representations on things that were like Kähler manifolds, but which could have this Nevers-Schwarz 3 form flux. And this is what they found. Any questions about this? This is how they presented the geometry. And we're going to call this, we tend to call this nowadays a bi-Hermitian geometry. Some kind of bi-Hermitian geometry. Okay, now I just want to point out something pretty crazy about this set of equations. So these equations are kind of hard to understand. Again, we're going to see an alternative way of thinking about them in a few moments. But there's an important consequence of this. So so take a look at this equation. You see that we have ddc. Forget about plus and minus, just to focus on one of them. Let's say we focus on omega plus. So ddc omega plus is equal to 0. Okay. Let me just ignore the plus minus. So if we have a form like this, right? This is another way of saying this is dd bar omega is equal to 0. So we have a 1-1 form, which is dd bar closed. Now if we focus on this thing, this quantity is del closed, and it is del bar exact. Okay? And so this is a perfect element of the differential forms to apply the dd bar lemma to. dd bar lemma says that if you have a form which is del closed and del bar exact, then it's del bar exact. So it would say that del bar omega would be del of something. Okay. So and in that case, this H, this would imply that the cohomology class of H is 0. Okay. So the interesting thing here is that if this closed 3 form, if the Nevers-Schwarz 3 form of this model was non-zero in the Ram cohomology, then the dd bar lemma cannot possibly hold. The D-bar lemma is obstructed. And therefore, we cannot have it cannot be algebraic. So the complex structures, I plus minus, are non-algebraic if the cohomology class of H is non-zero.
What does it mean, non-algebraic?
It means it's the complex manifold doesn't come from algebraic geometry. It's not a project. It's not a. Well, it holds for algebraic and a little bit more than that, but it definitely holds for algebraic ones. Yeah.
But not for all complex.
Not for all complex manifolds. So, for example, for example, if we take S3 cross S1, which is C cross C, which is C2 minus the origin mod the action of Z, you could express this in this way. It's a complex surface. It's called the Hopf surface. Okay, and it has no H2, cannot be algebraic, and the D-bar lemma does not hold. So you have this 3 form, which is the volume form of the S3, and that's a perfect example of one of these classes. It's a non-zero class in homology, and it is exactly of this type. It's D-bar exact and del closed, but it doesn't have, it's not exact. So there's an interesting thing that if you want to find examples of these where the 3 form is non-zero, it's very challenging because the type of complex manifold you have to deal with is not algebraic. Okay. Okay, so one of the key, one of the nicest aspects of Kähler geometry is that the metric, this symmetric tensor, complicated thing, is actually a formal consequence of a single scalar function, the Kähler potential. Okay? And this is something that even showed up in Samson's talk yesterday. But of course, that statement people are always fast and loose with that statement, because the real statement is that you need this scalar function, but you also need the complex coordinates. You also need the complex structure in order to be able to convert that function into the metric, right? So it's not, yeah. So, right, so there was another, in that paper in 1979, Zumino made a second observation, which is related to the Kähler potential. And he said that, that actually, if you use the complex structure, which gives you this supersymmetry, and if you use it to upgrade your map to a supermap from a supermanifold, which is exactly what Samson was doing yesterday, right? He had this big sigma and this big phi, which included the bosonic part being, anyway, I think you know what I'm talking about. So if you extend it in this way, then the action of the sigma model, which normally the action would be, it would be the norm squared of the derivative of this map plus the Vestimino term plus maybe the fermionic fields and so on. So that complicated action becomes just this, the pullback of the Kähler potential by the supermap. So Zumino had already observed this fact that the existence of the Kähler potential allows you to write the Lagrangian theory in a very simple way. And not only that, but because you write it this way, it makes the supersymmetry manifest. Okay, because of the fact that this is just a real scalar value function, and so it's exactly as in what Samson was talking about yesterday, that since everything is just scalar on a supersurface, then the symmetry of that supersurface gives you the supersymmetry. So the main question that the physicists, one of the main questions that the physicists had, Gatesall and Rocek, was, there should be an analog of the Kähler potential in this alternate model, this bi-Hermitian model. And so there are many papers devoted to solving this question, and what they were able to do was to solve it under very strong assumptions on the behavior of this bi-Hermitian structure. So, for example, under the assumption that I plus and I minus commute, they were able to solve the problem. Or that's the main, or, well, yeah. So you see what I mean, that they're making very strong assumptions on the type of target in order to be able to produce that K. And what we wanted to do was to finally remove that kind of restriction and to try to understand this model a little bit better. Okay, so is the question clear? Because that's what I'm going to answer today. Ask questions at this point.
So this is a local statement, right?
Yeah, I find that's a very good point, and I like that question very much because I think that in order to describe the global meaning of this, you need to do something more clever, and the hint of that will come later. Yeah. Okay, so the main tool that Hitchin and I introduced, which turned out to have an impact on this type of geometry, is called generalized complex geometry. Instead of having a complex structure on the tangent bundle of a manifold, you get a complex structure on the sum of the tangent and the cotangent bundle. There's a natural metric on this, which is of split signature, where the norm of a vector plus one form is just the evaluation. And so that you should think of T plus T star as a generalized version of the tangent bundle. Now here, how do you know when a complex structure of this type is integrable? Well, you find the plus I eigenbundle, and you require it to be closed into the Lie bracket. Here you can look at the plus I eigenbundle inside T plus T star, and you can use a bracket which exists here, which is called the Courant bracket. It basically is an upgrade of the Lie bracket. We have the Lie bracket, and then we have some natural operations which involve Lie derivatives and so on. And the interesting thing is that you can use the 3 form to modify the bracket. So this bracket incorporates the Nevers-Schwarz 3 form flux. There. And just to give you a kind of a sense of maybe a little bit more detail, here in the complex case, for the case of a complex manifold, there's the very famous canonical line bundle, which is the bundle of N0 forms. Okay. And these N0 forms, they're characterized by the fact that the 0, 1 vectors, when I interior product on this N0 form, I get 0. So this is an interior product here. Similarly here, there would be a line subbundle of the complexified differential forms where this L kills this line bundle. So this line bundle is defined by the fact that it's annihilated by the action of L. What does this mean? Well, the way that an element in T plus T star acts on a differential form is by interior and exterior product. This is the Clifford action. It's a Clifford action whereby the Clifford algebra of this metric bundle acts on differential forms, and it turns out that the differential forms can be viewed as spinners for this metric bundle. So just in case you haven't seen these things before, here's some examples. So if, is there a stick? But I have to be careful not to break the telephone. So, okay. So here, if I is a complex structure, you can allow it to act on T, and you can allow its dual to act on T star, and then it will be a block diagonal generalized complex structure. Here, this minus sign is necessary in order for it to be compatible with the natural inner product. And here we have the plus I eigenbundle, and the canonical line bundle is just the usual canonical line bundle. So we reproduce the complex case. And similarly, if we have a symplectic form, we can think of the symplectic form as defining a map from T to T star. That's this so-called musical isomorphism, apparently. And then its inverse would go from T star to T, and so you get an off-diagonal example. Okay, and this is the plus I eigenbundle. The plus I eigenbundle is just the graph of omega, roughly speaking. And the canonical line bundle is exactly the line bundle generated by the exponential of I omega. So this is a differential form of mixed degree, 0, 2, 4, etc. And that is the line bundle corresponding to to this generalized complex structure. So you can see that the same structure is interpolating between canonical line bundle of a complex manifold and e to the I omega, which is a kind of maybe familiar from mirror symmetry. And here's the interesting example that we need to talk about today. So if you can find on your complex manifold a holomorphic Poisson tensor, the holomorphic Poisson tensor is a bivector field which satisfies the Jacobi identity. And this thing is it's a holomorphic Poisson structure. It's a holomorphic Poisson bracket on your complex manifold. And this thing has real and imaginary parts. Because it's holomorphic, it has real and imaginary parts. The imaginary part is Q, I call it. And you can put it here in the upper right corner. So now this is an upper triangular generalized complex structure. The fact that this squares to -1 is a consequence of the fact that Q is the imaginary part of something in wedge 2 T10. So there's an automatic compatibility between Q and I, and that guarantees that this thing squares to -1. The plus eigenbundle is written there, and the canonical line bundle is the same as before, but you have to act upon it by exponentiating the interior product of the Poisson tensor on this. So this will again be of multiple different degrees. Okay, so this is a very important fact, that any holomorphic Poisson structure can be viewed as a deformation of a complex structure to some kind of generalized complex structure of this form. So we are now going to think of holomorphic Poisson tensors as deformations of complex manifolds into generalized complex manifolds. Any questions about
Exponential sigma is now a contraction with a bivector.
Yeah.
So it's n form, n-2 form.
Correct, yeah. Okay, so here's the way that, okay, this was work that I did in my thesis. I explained that actually, and this came as a shock to both of us, Hitchin and I. We were not expecting this at all, and in fact, I had never heard of this bi-Hermitian geometry, but in 1981, when Hitchin was visiting Rocek, Rocek was telling him about this bi-Hermitian geometry, and Hitchin couldn't make any heads or tails out of it, and so he just stored it in the memory bank and worked on something else. And then when I was a student, he took it out of the memory bank and said, look at this paper by Rocek, maybe now you can understand it. So the point is that we can take these structures, this bi-Hermitian structure, and we can create a generalized complex structure. We can create two of them with the pluses and the minuses. So it turns out that this structure has an alternative expression as a pair, bold I plus, bold I minus, of generalized complex structures on the same manifold. And the fact that I plus and I minus are both Hermitian with respect to G, it implies that these two generalized complex structures actually commute. So these complex structures are very far in principle from commuting. They might commute at one point and they may not commute at another point. They're not algebraically related in any way, these two complex structures. But when you combine them in this way, they commute. Okay, and then what you can do is use both of them just in the same way that on a Kähler manifold. Right, we have two structures. We have the complex structure and the symplectic structure. And the compatibility implies that we get a metric. Right? So similarly here, if I have two commuting generalized complex structures, I can combine them together with the natural inner product to get something which is another symmetric tensor. And so we say that this defines a generalized Kähler manifold when this thing is positive definite. Okay, so summarizing, the idea is that if you have one of these bi-Hermitian geometries, 2,2 geometries, you can reformulate the structure into a pair of integrable GC structures commuting such that they determine a generalized metric on the sum of the tangent and cotangent bundle. Okay? And the cool thing is that the Nevers-Schwarz three-form flux, this H, right, is what is used in the Courant bracket for which these are involutive, or integrable. So the three-form flux, it occurs in the integrability condition of I plus and of I minus. And they're both integrable with respect to the same H, the same three-form. Okay, so I could give a very elementary explanation for where this comes from, where this matrix comes from, but that would take a long time, and it wouldn't be. That's not the point of this talk. So if you want, you can look in my paper on generalized scalar geometry, and then you'll see the explanation. Okay, so when we started studying this generalized scalar geometry more carefully, we started to find that embedded within it, very different from Kähler geometry, embedded within this geometry is a whole bunch of Poisson structures. Okay? There's two important real Poisson structures, and there's one holomorphic, and there's two important real Poisson structures and two important holomorphic Poisson structures, and they're different. Okay, so it turns out that when you form these combinations, so this combination of the sum of the complex structures and the difference of the complex with the metric, you get a skew-symmetric bivector, which is actually Poisson. Okay? So you get a Poisson structure and another Poisson structure, and what I tried to draw here is the leaves, the symplectic leaves of these Poisson structures. Okay? And the point is that they are transverse. They're not complementary, they can intersect, but the sum of their dimensions is the full dimension of, they're transverse but not necessarily complementary, so that means that they sum to the whole tangent space at each point. Okay? So and also these leaves, they don't have to be of the same dimension. They're symplectic leaves of a Poisson structure, so they could jump in dimension. Okay, so the idea here is that these, the A I drew in red, the B I drew in blue, and the intersection between these two symplectic leaves, that gives another foliation. And that foliation is the foliation of this one. This one, which is the combination of the metric with the commutator of the two. And it turns out that this one, and this is something that Hitchin observed in his paper on the topic, these are holomorphic Poisson structures. So the idea is that we have two real Poisson structures, and their intersection has a holomorphic structure. Okay, and how does this specialize to the usual Kähler geometry? Well, the way that it specializes is that one of these Poisson structures is just the inverse of the symplectic form, and the other one is zero. So that means that for one of them, the foliation is by points, and for the other, the foliation is by the entire manifold. So we have an extreme case, which is the Kähler case. Okay, so there's an obvious question: is it possible to take a Kähler structure and to deform it? I mean, the obvious question that you might ask is: does there even exist any of these bihermitian structures? Does there exist a generalized Kähler structure? I mean, that's not obvious from these equations. But maybe a related question is: can we deform a Kähler manifold into a generalized Kähler manifold? So let me just give you. It's not important for the rest of the talk to understand the details of this construction, but let me just explain one of the constructions that I use to construct examples of these. So if you start with a Kähler manifold, let's say CP2, okay, and on CP2 we have plenty of Poisson structures, holomorphic Poisson structures. That's what I'm going to use to deform, because think about it in reverse. If I'm trying to produce a GK structure, I know that I need to have a holomorphic Poisson structure in the end. So I might as well try to construct one by starting with a holomorphic Poisson structure. It's like reverse engineering, right? So I start with a holomorphic Poisson structure, which is a section of wedge 2T. Wedge 2T in dimension 2, that's just one dimensional. This is just a section of O3, so it's a cubic polynomial. A cubic polynomial. And here I drew the zero set. So the Poisson structure is a cubic polynomial, and it vanishes, the Poisson structure vanishes on a cubic curve, or an elliptic curve. So the symplectic leaves of this thing, are this entire complement is one big leaf, and then all the points along the zero locus are the other symplectic leaves. So the symplectic leaves have dimension 0 or 4. It doesn't have a dimension, there's nothing in between, because this is a holomorphic Poisson structure. So you can't have. Anyway, so then what are we going to do with this? So we're going to take the Kähler structure, and we're going to try to deform it using this holomorphic Poisson structure. And the way that we do this is pretty cool. We combine the Poisson tensor with the Kähler form, okay? And then you can see that when you smash these two things together, the indices add, so you get H1. I'm thinking of the Kähler form as H1 omega 1. It's a 1-1 form, okay? And then this one form contracts against the bivector, and you're left with T. But H1T, that's the deformation space for the manifold, and if we're on CP2, this is 0. So that means that sigma applied to omega is Dolbeau exact. So that means that there must exist a potential for this thing. That d bar of this V is this contraction. And you can prove that you can also choose that V. What is V? V, you see, like this class here is in H1 of the tangent. So that means that V must be a smooth section of the tangent. It's a vector field. It's a smooth vector field. Okay. So this is saying that there must exist a smooth vector field whose derivative is this class, this contraction. And what I'm saying is that you can always choose that vector field so that it preserves the holomorphic Poisson tensor. And this is a little bit of a weird thing, because this thing is holomorphic, but this is not. So this is a smooth vector field that preserves a holomorphic Poisson tensor. It's a little bit strange, but these things exist, and I tried to draw it here in orange. This is a vector field which is somehow moving around the CP2, when sigma is 0, in the region where sigma is 0, the Poisson structure is 0, then V becomes a holomorphic vector field along the elliptic curve. Okay? So this is very cool, because it means that we have an elliptic curve embedded inside CP2. We have a holomorphic translation on the elliptic curve, okay, which is important for all these things like the Skleanin algebra or non-commutative algebras built from elliptic curves. They're always using these kind of translations. But anyway, that holomorphic translation is being extended to the whole of CP2, but it cannot be extended holomorphically. It can only be extended smoothly. Anyway, that's the vector field that we use. And then we flow it for time 1, apply that to the complex structure, and we get another complex structure. Now we've got two complex structures, I plus and I minus, just by flowing by this vector field which was constructed from the Poisson tensor. Okay. And then, so that's basically it. The only thing that you need to check is what will be the metric, what will be the new metric. So that's a little bit more complicated. What you're supposed to do is take the original Kähler form and drag it for time s by the flow of this vector field. Okay, pull it back, right, for all times s, and average that. Average the thing you get by flowing it, right? And then you get a new two-form, a new closed two-form. And when you combine that with the complex structures over 2, that's very similar to this equation. G is minus omega plus I. Or Kähler, it would be like this. The metric is obtained from the Kähler form and the complex structure. Here we have this averaged Kähler form, which is a closed form, and combined with the average of the complex structures. And this gives the metric a metric which is compatible with these two complex structures. Okay. So this is another one of those constructions that we obtained it from some natural reason, but in the end it looks very ad hoc or bizarre. I don't have time to explain it, but this is an explicit way of producing an example.
Just a question, so you're saying it's an explicit way. Are there some situations then you can actually integrate those vector fields, right? Because that's
Absolutely,
how,
yeah, absolutely. You can even find formulas for the metric, but yeah, you can certainly work in coordinates, and sometimes if the Poisson structure has particular symmetry, like for example, we could have chosen a Poisson structure which is toric, let's say, then it would be particularly easy to integrate. Yeah.
But you need integration along the elliptic curve?
No, you would need it along everywhere for this. Yeah. So anyway, this is a way of producing the generalized Kähler structures. And actually, another class of examples which you should be aware of is if you take G, a semi-simple, even dimensional real Lie group, then you can take a bi-invariant metric. You can take and you can choose a complex structure on the Lie algebra. You can choose a complex structure on the Lie algebra, and you can left translate it, and you can right translate it. And it turns out that this will be generalized Kähler, and with H being the Cartan 3 form. Okay, so for example, these things would exist on S1 cross SU2, which is the Hopf surface. It also exists on SU3 cross SU3. This one has been studied. Oh, sorry, SU2 cross SU2. This one has been studied, and SU3 even. You don't usually think of SU3 as being a complex manifold, but it is actually a complex manifold. It has 8 real dimensions, but it's a complex fourfold, it turns out, in 2 different ways, I plus and I minus. So we have a large number of examples of these structures.
So the complex structure on Lie algebra is supposed to be compatible with the bracket?
Yes, there's some conditions here, yeah. I haven't, it has to be compatible with the bracket, and it has to be adapted to the Cartan subalgebra as well. So you need to choose a complex structure on the Cartan subalgebra, extend it to the Lie algebra so that it preserves the root spaces. Yeah. Okay. So that was the introduction to generalized Kähler. And now we're going to get to the potential, the issue of the potential. Can you remind me about what's my target?
say 11:15.
Okay.
Would be a good target.
Okay. So, in order to understand the idea that I'm going to present, right, I need to teach you something. I need to teach you about something that you already know very well, which is Kähler geometry. I'm going to tell you something about Kähler geometry, which is coming from an observation in one of Donaldson's papers in 2001. This was just a kind of small remark, but it was very influential for the study of Kähler-Einstein metrics and constant scalar curvature Kähler metrics. Anyway, so he made the following observation. He was saying something like this. Suppose that you choose local Kähler potentials on a Kähler manifold, K alpha. Okay, then what you get from this is a bunch of 1-0 forms by taking del K alpha. I'll call those A alpha. And A alpha is of course not holomorphic because d bar of it is the Kähler form. So its d bar is not 0. Okay? But because the Kähler form is global, that means that A alpha minus A beta is killed by d bar. And so this is holomorphic. So what we get is a holomorphic 1 form on double overlaps for your check cover. So we get a class in H1 omega 1, and this is the Kähler class. It's another way of writing the Kähler class. But he said, okay, take this Kähler class, and let's build a space from the Kähler class. Let's represent the Kähler class, not as an element, not as a form, but as a space. Okay, how do you do that? Well, you take the cotangent bundle, the holomorphic cotangent bundle, that's why it's curly, and you break it up into pieces, T star U alpha, T star U beta. You break it up, the cotangent bundle, and then you glue it back together. But when you glue it back together, you don't send these momenta and positions to the momenta and position. You send it to the same position, but you increase the momentum by this A alpha beta. So you translate, you glue this to this with a vertical translation. And because this forms a cocycle, all these gluing maps will be consistent and you'll get a new space. Okay? This new space is called the twisted holomorphic cotangent bundle. And we call it Z. So this is a picture of it now. Okay? So notice that because you are gluing pieces of the cotangent bundle by this vertical translation, that means that the zero section is lost. The zero section is ruined by this. So we no longer have a zero section, there is no zero section, and it's not a vector bundle anymore, because a vector bundle has to have a zero section. Okay. Instead, it is what's called an affine bundle. It's a bundle of affine spaces for the cotangent bundle. So the cotangent bundle acts on this thing, but it is not this thing. Okay? And not only that, but because we are adding, because the translation is adding these A alpha beta, and these A alpha beta are closed, holomorphic one forms, that means that the gluing map preserves the natural symplectic form which exists on the cotangent bundle. So that means that now we get a holomorphic symplectic form on this twisted cotangent bundle. Okay? Because although the zero section is ruined, the holomorphic symplectic form on the cotangent bundle is not ruined by these gluing maps. Okay, so we've got now an affine bundle with a holomorphic symplectic form on it, which is acted upon by the holomorphic cotangent bundle. Okay, and so all of that is holomorphic data. We have a holomorphic affine bundle with holomorphic symplectic form. Okay. So from this holomorphic data, we are not going to get a Kähler metric. Right? The Kähler metric is infinity data. We're not going to be able to get it from algebraic geometry. So there's got to be something else. There's got to be something non-holomorphic in this picture which will generate the metric. And the incredible thing is that, well, I mean, it's very easy to see. You see, instead of just the A alpha betas, I need the A alphas. I need to understand the original A alphas in order to reconstruct the metric. And if we take the graph of the A alphas, I mean, the A alphas, they were not global before, they were local, because A alpha minus A beta was A alpha beta. So before, they were local, and the discrepancy was A alpha beta. But now we've eaten up the discrepancy in the construction of the space. So that means that now it's global. So now we have a global cross-section of this bundle, and this global cross-section is C infinity, because the A alphas, remember, they were not holomorphic. Okay, so by taking the graph of the del of the Kähler potential, right, this thing which used to be local now becomes a global section. And what happens when we take this holomorphic symplectic form and we pull it back to this cross-section? Well, if you pull it back, okay, it's always the same in a cotangent bundle. If you take the canonical 2 form and you restrict it to a section, you're going to get the derivative of the section. That's why it's called the tautological form. This thing gives the derivative of whatever that section is. And that derivative is the symplectic form. And that symplectic form is real. So this was not real, but this restriction to L is real. Okay, so that means that omega has 2 parts. It has the imaginary part and the real part. The real part restricts to the Kähler form. The imaginary part restricts to 0. So that means that this cross-section is at the same time Lagrangian, because of the fact that the imaginary part of this symplectic form vanishes, but it's also symplectic for the real part. So Donaldson called these LS submanifolds. Okay, but we know from the study, we know that another way of thinking about it is that you could think that really we'll focus on the imaginary part and think of that as a symplectic manifold, and we've got a Lagrangian, an A-brane, a Lagrangian submanifold. So in other words, this observation, what does it say? It says that the Kähler metric is a Lagrangian submanifold. a real Lagrangian submanifold. And when you see that, then it becomes very clear why Kähler metrics have a single scalar degree of freedom, because any Lagrangian submanifold, can be moved by the derivative of a function, a single function. Okay, so this gives, in my opinion, the most beautiful explanation for why Kähler metrics are the way they are. It's because they are Lagrangian submanifolds of a real symplectic manifold. Here's an example. We have if we take the Fubini-Studi-Kähler structure on P1, we can absorb that into the construction of a twisted cotangent bundle. The twisted cotangent bundle turns out to be an affine quadric surface. It turns out to be a two-dimensional complex manifold. I tried to draw it here. It's like a hyperboloid, okay? And it has a holomorphic symplectic structure, which we write explicitly. And then the real locus of this is a sphere, a two-sphere. Okay? And this real locus inherits the Fubini-Studi metric. So we can think of the Fubini-Studi metric as an S2 embedded as an imaginary Lagrangian submanifold of this algebraic quadric. And so you could think that by wiggling this thing around, by moving it around, you're changing the Kähler metric. It's a kind of remarkable way of thinking about it. Okay, so that concludes the review of Kähler manifolds. This is something that maybe we should have been taught, but we never were, about how to think about a Kähler metric. You can think of it as a Lagrangian submanifold of a holomorphic symplectic manifold, which is constructed from the Kähler class. The Kähler class is represented by the complex manifold and its holomorphic symplectic structure, and then the Kähler metric inside the Kähler class is described by a Lagrangian. Okay, so why am I telling you this exotic description of Kähler geometry? The reason is because it turns out that after so many years of trying to solve this problem, this is the interpretation that we needed. This is the interpretation that generalizes to the generalized Kähler. Okay, so we needed to think of it this way in order to be able to see how to solve the problem. So what are we supposed to do in general? So it turns out that in general, the picture will be exactly the same. It's just that we need to know what's the analog of this twisted cotangent bundle. What's the analog of this holomorphic symplectic thing, which is of twice the dimension and which covers our manifold? Well, the hint comes from the fact that in general, we know that there should be a holomorphic Poisson structure. So if we now think of the base, right, the base manifold, as if it was holomorphic Poisson, then that Poisson structure has a symplectic groupoid associated to it. Okay, and so this was studied in the Weinstein school. The symplectic groupoid is a holomorphic symplectic manifold, right, covering the Poisson manifold, okay, in such a way that the symplectic structure pushes down to the Poisson structure. So it's a way of seeing this Poisson structure, but converting it into something non-degenerate. So this space has a projection map down here, and that push forward of the symplectic form is this Poisson structure. But then the cool thing you can do with such a map is you can take the symplectic orthogonal of the fibers, and the symplectic orthogonal gives you a distribution. That distribution is involutive, and it gives you a new map, and you can push forward the symplectic structure. It is push forwardable to a new Poisson manifold. Okay, and so this thing is actually it's a holomorphic symplectic manifold that relates two different Poisson manifolds, and it's what they called a Morita equivalence. A Morita equivalence between Poisson structures. Okay, so maybe I won't finish what I had planned, but let me give the theorem. So the theorem is that, so we're going to, there's a simplifying assumption which we needed to make because otherwise the result is much more complicated and hasn't been written down. That if we make the assumption that one of the two Poisson structures is invertible, and the other one doesn't have to be, it could be anything. Okay. Then we have what's called a generalized Kähler structure of symplectic type. just because this inverse gives a symplectic form. And what we showed was that, that the generalized Kähler structure determines and is determined by the following picture. We have a holomorphic symplectic manifold, which plays the role of the twisted cotangent bundle. And there's holomorphic Poisson maps to the two Poisson manifolds that we have in theory. So we have now complex Poisson, complex symplectic. And this complex symplectic is it's a Morita equivalence between these two Poisson structures. And then in order to get the metric, we need to choose a Lagrangian bisection, which is C infinity. And it's exactly in the same way that this real Lagrangian submanifold reproduces the Kähler metric. You can kind of see how it goes like this. So for example, when I choose this section, you end up, this section determines a diffeomorphism between the two sides, because I can take a point, go up, find the point where it intersects, and then go down. That defines a map like this. You could think of it like a mirror. You look and you see the other complex Poisson manifold, and therefore these become now on the same manifold. And you get two complex structures on the same manifold, which is what you needed. Okay. The other thing is you need a metric. How do you get it? You take the holomorphic symplectic form and you restrict it. You get a 2 form. You take its 1-1 part with respect to the plus, combine with I plus, or the 1-1 with respect to I minus, and combine with I minus. These agree. These symmetric tensors agree, turns out, because of the properties of this Morita equivalence, and we get a symmetric tensor, and we require that that is positive definite, and that's exactly how you recover this generalized Kähler structure. So it's a kind of, you can kind of imagine that what's happening is that, originally this space was the twisted cotangent bundle, where the red and the blue lines are all parallel, and they're just the projection down to the base. Okay, and then when you turn on the Poisson structure, these things separate, and they become different. Okay, but still, it's true that we can choose the cross section, and we get a metric from it. Okay, so I'm going to use this tomorrow, but I have to stop. Thank you.
Questions or comments?
Does this symplectic realization always exist?
This is studied. I mean, I don't mean to say this in an insulting way. I think it's a good thing that this thing has been studied to death. Yeah, I mean, you can find N papers about when do these symplectic realizations exist, how big are they, and so on. The idea is that whenever you have a Poisson structure here, you can always create a local realization. You can create a kind of a tubular neighborhood with a symplectic structure that maps down. So you can always do that, but the problem is that it won't be, it'll have this annoying property that if you take functions and you do Hamiltonian flows, the Hamiltonian flows won't be complete upstairs. So what you'd like is you'd like to produce a realization, at least what's important for a Morita equivalence, for a genuine Morita equivalence, is that you would need it to be a complete realization. And the complete realization may not exist if you're dealing with very exotic Poisson structures. But actually, for most Poisson structures that I have met in real life, they always exist and they're always,
What I mean is that you obtain a holomorphic symplectic realization. Isn't it something more?
I'm sorry?
You obtain a holomorphic symplectic realization.
Yeah, but that's just because the Poisson structure is holomorphic. So everything carries through. It'd be just you have to add the word holomorphic. Yeah. Yeah.
Okay, well, Marco, thanks again.
Okay.